Right. A very good morning, our dear viewers. You are welcome to today's segment of homeschool program. This is a program that has been running for a quite number of days since the quarantine time started. We are so grateful that our dear directors, Pastor Jackson Senyonga and Pastor Eva Senyonga, they were able to allow our learners to continue studying even when they are at home. So our dear parents, viewers, and everyone who is outside there, the one who is not studying, please make sure you encourage those students to always wake up early and attend to these lessons. Activists who are there, please also do the activism work of inviting everyone to attend these lessons. If you know that you have reached somewhere, at least make sure you encourage your brothers and sisters to also reach there. Okay? Before we start this lesson, I'm your teacher today, Saul Abooki, and I will be taking you through more concept in chemistry. And majorly we shall look at molecular theory of gases. Today we are going to put our focus on this one, molecular theory of gases, okay? And always I've tried to make sure that I remind you to do the following. If we look at our slide, we are looking at a number of things. Please make sure you have a notebook, you have a pen, you have a calculator. I've always told you you be with a functioning calculator. Okay? Also, if you have been missing lessons or if you are not able to access this work in time, you can still visit our website www.kodaiSchool.ac.ug. You can visit our top television page on Facebook. You'll be able to access these videos and you learn again. If you learned and you didn't understand some things, you can review the videos and you again look at those things. Okay? Before we start, make sure everyone is alert. Make sure you invite those brothers, those sisters. Tell them to come near to the TV. Tell them to be with everything. And we start our lesson today. Let us begin our lesson. We have said the topic is mole concept, and the subtopic that we are going to be handling today is molecular theory of gases. Okay? So that's what we are going to be looking at. On our next slide, we have to first look at what we did yesterday, because it is very important to look at what you have done so that you'll be able to use it to study what you don't know. Okay? So we are going to begin with what we did yesterday, and that is what we covered. We looked at calculating masses from equations. We calculated a number of things here, and we were able to achieve that. However, if you didn't get a few things very well, this is the right time. You're going to understand everything. We looked at what they call the stoichiometric equation, and we said that one is an equation that involves reactants and products where they are well balanced. Okay? We look at the products and the reactants, they are correctly balanced. And we said that balancing an equation does not mean that you involve figures. There are equations which are already balanced. So you don't need to write a lot on it. You just need to look at it and you compare the atoms in it. So we said in calculating for masses from equations, we look at a number of steps. One, we said the first thing we do is to write the equation. Or after writing the equation, you look at it. Is it balanced? If it is balanced, that one qualifies to be the stoichiometric equation. Then you go to the next step. You write the moles. You look at the numbers which are on that equation. The numbers before any compound or before any substance there. Those are the moles. Then you convert the moles into grams. You know, we say that in chemistry we need to do things practically. So we can look at the steps, but if you don't apply those steps, you may not know them. So let us look at our next slide and we see one of the examples you can use to apply those steps. We looked at that one. We said calculate the mass of copper formed when 3.2 grams of copper 2 oxide is completely reduced to the metal by hydrogen gas. That was part A. That means here we are going to be calculating for copper. And remember, copper is being formed from copper 2 oxide when copper 2 oxide reacts with hydrogen gas. Then part B is saying how many grams of water was produced. Part C is saying calculate the mass of hydrogen used in the experiment. When we go to our next slide, we are going to see the steps that we can follow to get the correct answer. We have to first write the equation, and that is the equation. The equation is copper oxide, and that is the chemical formula of copper oxide, reacting with hydrogen gas, and hydrogen gas is H2. Okay? Hydrogen gas is different from hydrogen atom. So when you react the two, you come up with copper solid. Copper, just copper alone. Then you have to produce water. You release the water molecules. Okay? When you try to balance that equation, you see that copper, you have one atom of copper producing one atom of copper. You have one atom of oxygen producing one atom of oxygen. Two atoms of hydrogen producing two atoms of hydrogen. That means the equation is well balanced. But remember, the question is requiring us to calculate for the mass of hydrogen that was used in the experiment. Okay? Remember, hydrogen is reacting with copper oxide. And when you look at the equation there, you see that copper oxide plus hydrogen, it is 1:1. So we shall say, remember we have copper oxide. So we put copper oxide on our left hand side. We begin with it. 1 mole of copper oxide reacts with 1 mole of hydrogen. Okay? And we said we change moles into, we have to change those moles into grams. And we said 1 mole stands for the RFM or the RAM, relative atomic mass or relative formula mass. And now the relative formula mass of copper oxide is, you get copper 64 plus oxygen 16. Okay? Then you say that copper oxide reacts with hydrogen. Hydrogen is 1 times 2. There are 2 atoms. Then you get 8 grams of copper oxide. You say reacts with 2 grams of hydrogen. And remember, we said that once you have the grams, you have to turn them to 1. If 80, they are reacting with the 2. What about 1? That means 1 will react with 2 over 80. Then you say, what about 3.2, the one which has been given the question? You end up getting the right answer, which is 0.08 grams of hydrogen. And hopefully that you have been practicing that. I never wanted to repeat it on the blackboard because that's what we did yesterday, and you all have it. Only that I came with a slide so that you use the slide to reflect on what we did yesterday. Okay? So very quickly we shall go to what we are supposed to achieve today, and that's what we call our objectives on our next slide. Okay? We look at our objectives. We say that before or by the time, okay, this lesson ends, we have to achieve two things. We have to achieve to make sure that we are able to describe the two ideal gas laws. Okay? We look at the gas laws, and we have to make sure that at least by the time this lesson ends, we are able to describe them fully and use them in calculations. Then the second objective is we are able to apply the ideal gas equation. Remember when we state the laws, these laws are going to help us to get the equations. And once we have the equations, then we shall go into what we call mole concept, determining the number of particles. That means we shall start calculating for the number of particles. Okay? Those are our two objectives that we are going to look at. Now, having seen the objectives, let us move straight to what we are supposed to cover today. We are saying today we are going to put our emphasis on molecular theory of gases. Okay? When you look at this one, when you go to this theory, you find out that gases, the behavior of gases, when they are subjected to both temperature, when they are subjected to temperature and pressure changes. Okay? Want to see the behavior of gases when they are subjected to both temperature and pressure changes. Okay? And how can we express those ones? We are saying that when these gases, the behavior of these gases are subjected to the two, okay, we come up with, we can express the behavior into two laws, and that is the Boyle's law. We have Boyle's law and Charles's law. Charles' law. Okay? So we are going to use the two laws to express the behavior of gases when they are subjected to both temperature and pressure changes. And we are saying that these laws, they only apply to ideal gases. Okay? I want to write the keywords that we are going to be using today. We have ideal, ideal gases, okay? Behavior of gases, okay? When they are subjected to temperature and pressure changes, we can express that one in two laws. In two simple laws. These are simple laws. Right? Then we are going to look at Boyle's law and Charles' law. Okay? At the end, we shall achieve our objectives. Remember, there are two. Okay? Describing the laws and applying those laws. Then we are saying these laws only apply to ideal gases. And we can ask ourselves, what are ideal gases? These are gases with negligible intermolecular attractions. Okay? These are gases with negligible forces of attraction and negligible volumes. We can look at gases with negligible forces of attraction, but as well as they also have negligible volumes. Okay? So they have the two things in them. Okay, negligible. And we are saying that means the volumes are very small, even you can neglect them. Okay, we may not consider them. Okay, that's what they mean by ideal gases. So these are the gases we are going to be looking at. Okay, so with that, I hope we can go to our next slide and see and look at one of the laws. Okay, we have said that the behavior of gases when they are subjected to temperature and pressure changes, okay, we put that one into two laws, okay? That is Boyle's law and Charles's law. And we're going to see which law is looking at the change in temperature and which law is focusing at the change in pressure, okay? Then we have said that these laws only apply to ideal gases. And ideal gases, we are saying these are gases with negligible forces of attraction and negligible volumes, okay? These are the gases we are going to be dealing with. So with that, we are saying that let us go to our very first law and we see what is it saying, okay? On our next slide, want to look at the laws, okay? That is Boyle's law. Boyle's law is our very first law. We are saying that the volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. The volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. Remember we said we are looking at two things here. Now, if we first keep the temperature constant and we will see volume varying with pressure, we shall say that they are inversely proportional. Okay? Let us look at two things. In molecular theory of gases, we are going to be looking at three things. We are going to be looking at volume, we are going to be looking at temperature, we are going to be looking at pressure. Okay? What brings about the laws is the change in the two. Okay? So we are saying that once you vary volume with pressure and you keep temperature constant, that one we shall call it Boyle's law. And we are saying the volume, it says that the volume of a given mass of a gas is inversely proportional. Can we apply that one mathematically? We can say let us look at Boyle's law mathematically. Boyle's law, it is saying that volume of a given mass of a gas is inversely proportional to pressure. Okay? Here we can say volume is V, temperature is T, pressure is P. Okay? Can use those symbols. So here we shall write that mathematically. We say volume is inversely proportional to pressure. Inversely proportional is 1 over that thing, okay? Over what you are terming to be inversely proportional. Okay? So here, this is the proportionality sign. We have to remove it and involve in and we put in a constant. Okay? So we shall say that volume will be equal to constant. Okay? Because when we remove the proportionality sign, we introduce the constant. Okay? We say constant times 1 over P. Okay? V equal to constant times 1 over P. We want to put this law, we want to write it mathematically. Okay? Boyle's law states that the volume of a given mass of a gas is inversely proportional. We have done it. And we are saying that we are removing the proportionality sign, we are involving a constant. with equal signs. Then when we have this, then we can here, it is 1 divided by P. But when we want to remove this one from being a denominator, okay, we can multiply it on both sides. We multiply it here, we multiply P there, and we multiply P here. Okay? Then we get PV is equal to a constant, is equal to constant. Okay? So we are saying that PV is equal to constant. That means if you multiply the pressure with volume, the value will always be constant. Even if you vary it, you say, now let me change pressure, and if that means this one shows you, when I say that volume is inversely proportional to pressure, it shows you that increase in volume will lead to the decrease in pressure. Here, if we look at this one, okay, let us first apply it here and see it practically. If we have V equaling to 1 over P, okay, let us say that P is now 1, okay? Okay, P is 1. P equals 1. That means V will equal to 1 over 1 equal to 1. That is one step. Let us see, we move from 1. Now we are either going down or up. We say that P equals 0.5. Okay? P is equaling to a half. Okay? When P equals a half, V will be equal to 2. That means when you decrease P, V will increase. Okay? All right. Let us also look at it here. When we say P is equal to 2, okay? If we increase P from 1 to 2, what will be V? V will be 1 over 2. That's what they mean by inversely proportional. Okay? They are not directly proportional, they are inversely proportional. That means that this one increase in this one will lead to the decrease in this one. Decrease in that one will lead to the increase in this one to keep the value constant. So if we come here and we apply our values there, we are saying that here P is 1, V is 1. P is a half, V is 2. P is 2, V is a half. We come and apply it here. We say P times V is a constant. So all here we shall get a constant. Because 1 times 1, 1 times 1 is 1. A half times 2 is 1. 2 times a half is 1. Okay? So you get it that it becomes a constant. Once you multiply P, which is inversely proportional to V, you always get a constant. Okay? Hopefully that one is understood. And we are saying that if so, okay, if we can bring back our slide, we see that we have already said that PV is a constant. Okay? PV is a constant. And now we are saying that an ideal gas at a pressure P1 occupying volume V1 can be made occupy volume V2 at a pressure P2. Okay? Let us come back to our blackboard. Okay? Here we are saying that this one, what you have here, is equal to what you have here, is equal to what you have there. Okay? If P is 1 and V is 1, what you get here will be a constant. Not so? Even here, if P is a half and V is 2, what you get will be a constant. If P is 2 and V is a half, what you get there will be a constant. So we come up with a conclusion that what you have in P1 multiplying with V1 will be the same as what you have in P2 when you multiply it with V2. That's how it came up. comes about, okay? That what you have in P1, when you multiply it with what you have in V1, what P1 times V1, you get what is in P2 V2, because you have got it here. We are saying that if this one is considered to be P1 and V1, and here P2 and V2, all these answers are going to be the same, okay? So that's how we get it. So in the case you are given 3 of these ones and one is not given, that means you can be able to calculate for it, okay? You can be able to calculate for it, and that's how we are going to be applying this law, okay, in calculations. Hopefully you have understood these steps. We began from here. We said, I want to emphasize these things: volume V, temperature T, pressure P. And we said that in this subtopic, molecular theory of gases, we are going to be looking at the behavior of gases when they are subjected to temperature changes and pressure changes. And we said that one is going to be expressed in simple laws. And those are what we call Boyle's law and Charles' law. We are going to be looking at the two things. Then we said that these laws only focus at what they call ideal gases. They only apply to ideal gases. That means if they apply to ideal gases, what are ideal gases? And we have said that these are gases with negligible forces of attraction and negligible volumes, okay? That is it. Then we went ahead to look at the very first law, which was saying that the Boyle's law was stating that the volume, the first thing was the volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. Remember, all the 3 things have to be applied, but this one we first keep it constant, okay? That means it is not changing, so we are not applying it here. We are saying V is inversely proportional to P. We are saying increase in P leads to the decrease in V. Decrease in P leads to the increase in V, and we have elaborated that one. And we have come up now with what they call PV is a constant. When you multiply P with V, you always get a constant value, okay? Once you have that constant value, and we have proved it here, we have said that what is here, P1, PV1, is the same as what is in P2, V2, and we have come up with a conclusion saying P1, V1 is the same as P2, V2, okay? Hopefully that one is understood. So we can move to our next slide, and we see then our next law. Let us look at our second law. We have taken much time on this one because there are very many things that we need to emphasize. So on our second law, we are going to move a bit fast because most of the things I've already emphasized them, and hopefully everyone has got the idea. So when we go to our next law, we are saying that one is Charles' law. We are saying the volume of a given mass of a gas is directly proportional to its absolute temperature. Is directly proportional to its absolute temperature at constant pressure. Charles' law. Charles' law. We have already talked about 3 things being involved: volume, pressure, temperature. When the temperature is constant, the pressure should be varying. So for Boyle's law, the temperature was constant. In Charles' law, the pressure is constant, okay? And we are involving another term, absolute temperature, okay? And we are saying volume of a given mass of a gas is directly proportional to absolute temperature, okay? Volume is directly proportional to absolute temperature, okay? And that's what we have here. Volume directly proportional to temperature. That means if the volume increases, even temperature is going to increase, okay? So we have volume directly proportional to temperature. Let us involve in now we remove the proportionality sign and we put in the equal sign. V will be equal to constant, okay? V will be equal to constant times T. V will be equal to constant times T. And if you look at the first law, we had to make sure that constant remains alone. So what we do here, we divide by T. We divide by T. We say V over T will be equal to constant. That is it. Remember, the law is saying that volume is directly proportional to absolute temperature. Increase in volume will lead to the increase in temperature. Decrease in volume will lead to the decrease in temperature. They are moving together. So let us prove it here using the same concept we used the other side. The other side we looked at, if we change here, we are saying that if V is equal to 1, T also will be 1. Okay? For you to get a value of 1. Okay, let us take an example. If this constant, if the constant is 2, okay? If the constant is 2, the other side the constant was 1, okay? If the constant is 2, that means what will be the volume and the temperature? You can guess and say V can be 4. That means T will be 2, okay? We start from there, okay? Let us start from there. V is 4, T is 2. We shall get a constant of 2. Let us see if you increase temperature, what will happen to volume? If you say T is equal to 3, what will be the V? Will V increase or decrease? V will automatically increase to 6. For you to be able to get 6 divided by 3, and you get your constant 2. Okay, let us see if we decrease the temperature. If we say T is equal to 1, what will be the volume? Okay, if we say T equals 1, volume will be 2. Look, have a look at this one. You are increasing temperature, volume is increasing. You are decreasing temperature, volume is also decreasing. Okay, so that's what we mean by being directly proportional to one another. Okay, volume directly proportional to temperature, right? So after coming up with this one, okay, we can group this one to be V1, T1, this one to be V2, T2, okay, V3, T3, so that we can be able to conclude. Okay, if we can go back to our slides, we can see that relating volumes and absolute temperatures of an ideal gas at different values, we conclude when we relate at different values, and these are the values I've already given. We have given V4, T2. Okay, this one was our initial value, and we said this one was giving us a constant of 2. And we wanted to keep that value constant here, but we had to vary the temperature. We increase the temperature for the constant to remain 2, volume will automatically increase to 6. We decrease the temperature for it to remain with a constant 2, volume will decrease. So we shall say that V1 over T1 will equal to V2 divided by T2. Okay? Always, we shall say that V1, if divided by T1, it will always be equal to V2 divided by T2. Okay? As simple as that. Okay? We shall move straight to our next slide. And we see absolute temperature. What do they mean by absolute temperature? This is the temperature at which the volume of gases would be theoretically 0. The volume of gases would be theoretically 0. Remember we said that in this we are dealing with ideal gases, and ideal gases are gases with negligible volumes. And now we are saying that the volume of gases would be theoretically 0. You determine it to be 0 because it is a very small figure. Okay? So it is almost 0. So we are saying that the temperatures, if we look at the absolute temperature scale, if we look at what they call absolute temperature scale, okay, we shall find that all temperature values are in Kelvin. Okay? And how do we change the temperature values to Kelvin? Okay? We just get the degrees Celsius. We add there 273, and the value we get will be in Kelvins. Okay? We have to add there 273. But when you read very many textbooks, you'll find there that this value is always given at 273.15. They normally give that value. Okay? This constant value. If you round off, you get 273. But for you to prove that you're a chemistry student and you're aiming at doing sciences, you can put this value in your head. However, I've always told you that these values are always there in the examination paper. Any standard paper will always come with these standard values. Okay? I will say 0 degrees Celsius equaling to this one. Okay? They will put it there. 0 degrees Celsius 273.15 Kelvin. Okay? So you go and pick it from there, because this one stands for 0. If the temperature is at 0 degrees Celsius, that means in Kelvin we shall say 273.15. If they are saying that the temperatures at 100 degrees Celsius, that means in Kelvin it will be 100 plus 273.15, and the answer will be 373.15 Kelvin. Okay? You need to convert. So anything, any number involving the molecular theory of gases, involving ideal gases, make sure that the temperatures are in Kelvin. Temperature values are in Kelvin. Okay? Once you put the temperature values in Kelvin, you'll be able to solve the number. All right? And it will be very simple for you. When we move, see what is on our next slide, we are going to see what they call the ideal gas equation. Okay? On our next slide, we are going to see the ideal gas equation. Okay? And we are saying that this equation was obtained by combining. You can obtain this equation by combining both Boyle's law and Charles' law. Okay? You combine. Remember, the other one is saying that the volume of a given mass of a gas is inversely proportional to its pressure. Okay? Let us go to that straight. we want to look now at the ideal gas equation. That's what we want to look at, the ideal gas equation. And we are saying that this equation, you obtain it by combining both Boyle's law and the Charles' law. Okay? I've said in a statement you can give is that if Boyle's law is saying the volume of a given mass of a gas is inversely proportional to its pressure, and the other one is saying is directly proportional to its absolute temperature. That means you say you will combine the two. Remember, this one is all about PV constant. Okay? This one is V over T constant. So we are going to use two methods to combine the two laws. Okay? Let's first leave this one and we go back to the theory part. If the volume, okay, we are writing it mathematically as we apply the theory, is Charles' law is directly proportional to absolute temperature. Okay? And Boyle's law is saying that is inversely proportional to its pressure. Okay? Are we combining the two? Volume, the two laws say that volume is directly proportional to temperature. And at the same time, another law is saying that volume is inversely proportional to its pressure. Okay? Directly proportional to its temperature, inversely proportional. Proportionality sign, and we put in the constant. We say V is equal to constant times T over P. Okay? T over P. Here we are going to just apply mathematics and we make the word constant to be the subject of the formula. Okay? We are going to make the word constant to be the subject of the formula. All right? How do we do that? Times T. Okay? Then we divide by T, both sides. We shall end up getting PV over T equaling to constant. PV equaling to constant. And from what we have just been doing, we have said once we see the word constant, that means we can alternate these ones and we say P1 V1 over T1 is equaling to P2 V2 over T2. Okay? And this is going to be our ideal gas equation. Okay? It is going to be our ideal gas equation. That one is very important, and remember, we have three things. We have that. We have P1 V1 equaling to P2 V2. We have V1 over T1 equaling to V2 over T2. So we are going to calculate different numbers depending on what they are requiring us to do. Okay? We are going to apply these three methods. We are going to apply that, we are going to apply this one, and we are going to apply this general one, which is called the ideal gas equation. If we move to our next slide, we shall see that this ideal gas equation is what we have just got. And what does it help us to do? It enables us to calculate the effect of change. Remember, we said the change is going to be in temperature and pressure. It's going to help us to calculate the effect of change of temperature and pressure on the volume of a gas. The volume of a gas is there, and we are going to be seeing how these things can be affecting it. If we change, here, look at this one. If we change pressure, automatically, if we have these values, and here we change one of them, even the rest will change to keep the value constant. Okay? If we change P, the rest will change. If we change T, the rest will change. So that's what we are going to see in our examples we are going to be looking at. Once you are calculating this one, you compare it with the stated temperatures and pressure. And in most cases, you have seen in our next slide, we can look at gas volumes are usually compared to standard values. That means they are usually compared to, let me write that. Okay? Gas volumes are usually compared to 0 degrees Celsius. And we said this one is equal to 273.15 kelvins. Okay? We also looked at what they say. We can look at 1 atmosphere. That means this one will be 760 millimeter mercury. Okay? These are the two things. Temperature, pressure. Degrees Celsius stands for temperature. Atmosphere stands for pressure. So once we have these two, we can term this condition to be the standard temperature and pressure, what we call STP. So when they say that at STP, that means they are referring to what they call standard temperature and pressure. They are referring to what they call standard temperature and pressure. Okay? When they say at room temperature, that is at STP. When they say at room temperature, that means atmosphere, we shall remain with 1 atmosphere, which is 760 millimeter mercury. But temperature will change. You measure the room temperature. In most cases, it's around 20 to 25 degrees C. Okay? You give any value here, it will be standing for the room temperature. Okay? Any of the two. So when we move to our next slide, we can look at our example number 1 that we can go through very fast, and we'll be able to apply all what we have been looking at. I know it is becoming a bit complex. I told you at the start that chemistry will keep growing. We started with very simple things, and now we are looking at somehow complex numbers, okay? Complex theory in what they call more concept, but it is easy since we are going to be applying some of the things you have studied before, okay? Now let us look at that first example on our next slide. A certain gas occupies, okay, if I can remove this one. Our example is saying a certain gas occupies. That means here we begin with P1, V1. A certain gas occupies. V1 is 211 cubic centimeter. Okay? At a temperature, T1 is 18 degrees Celsius. And we said that when we convert it to Kelvins, 273.15. What do we get? 0.15. Then we say pressure, which is P1. They have said it is 740 millimeter mercury. Okay? Then they are saying what volume will it occupy? Still gaseous at question now is involving T2 is negative 20. Okay? Which will be negative 20 plus 273.15, which is going to be, we said we may not use 0.15. This one, we can round it off. Okay? Normally, most questions don't involve them. Okay? You can just get the value. This one is 283, 291. Okay? This one here is 253 Kelvin. Okay? The question is what volume? And they have given us pressure to P2, which is 770 millimeter mercury. You can see how simple this question can be. Okay? You have been given all these ones, P1, V1, P2, V2, P2, T2. So what you do, you only substitute. You say P1 is 211, V1 is, P1 is 740 plus V1 is 211. It is times. This one is multiplication. Times that one divided by T1 is 291. We shall get P2 is 770 times V2. We have not been given V2. Divided by T2. T2 is 253. Okay? When you make V the subject of the formula, V2, you'll be able to get the right answer. Okay? When you make that one, you'll be able to get 176.3 centimeter cubed. You just need to substitute, then you struggle with making V2 to be the subject of the formula, okay? That is our example. And we don't need to get very many examples. From what we have explained, okay, this one is enough. The rest is just substituting. You are given, you substitute. Let us look at our last slide having the exercise, okay? That is the exercise. You'll go through it. What you have not covered today, the last slide, the very last slide. Please copy the exercise. If you are not able to copy it now, you can visit our website, that is www.codaischool.sc.ug. You'll be able to get the work all. Drop a comment on our top television page on Facebook. We shall be able to respond to you, and you'll be able to learn. Your teacher today has been Saul Chamanyo, who has been taking you through chemistry, more concept. We shall continue with the same concept tomorrow, 7 to 8 a.m. Let us meet there.